All right, section 3.1 kicks off a whole new chapter here for us in Algebra 2. And the entire chapter is called Linear Systems. Emphasis on the word systems, I guess, but obviously linear is also a very important part of that title. And section 3.1 is titled Graphing Systems of Equations. And I got this little sort of quote thing here at the start that says, "We're taking it up a notch again." It's kind of a homage to Seinfeld. I wonder what the chances are you've ever watched an episode of Seinfeld, but we're taking it up a notch again. And all that really means is that in mathematics and like Algebra 1 type stuff, and which also is included in Algebra 2, equations start off, very simple. And what I also mean by that is they only have like one variable, right? And then we can like keep taking it to the next level by, okay, what if we do inequalities where it's like a less than or a greater than, what if we throw absolute value in there and take things up a notch again. So it's like we keep on adding a new twist to all this like equation stuff and inequality stuff, and that we can kind of address that a little bit more in these couple of recalls. So this first recall from the past, the solution, that's a big word as well here. The solution to an equation such as x plus 5 equals 7 is the one number that makes the equation true when you replace the variable with it. So what would be the solution here? I'm sure you can think of it in your head that it would be 2. And that's because you could like replace the x with the number 2, and it would actually make the equation true. Like 2 plus 5 actually does equal 7. And so it's only one number, and there's only one of them. There's only one solution to this equation. It only has one solution to it. It's only 2 is the only number that makes this true. And then we talked about how you take that to the next level. When we talk about a solution to an equation such as 3x plus y equals 10. So now that there's both an x variable and a y variable, now the solution has to be a pair of numbers that makes the equation true when you replace the x and the y. So one number to go in for x and one number to go in for y. And looking at this, I could come up in my head an example of a solution. Let's say 1, 7. If x equals 1 and y were to equal 7, you'd have like 3 times 1 plus 7, which actually does equal 10. So 1, 7 would be a solution, but in this case, it ain't the only one. How many solutions are there to this equation? In other words, how many pairs of numbers would make this true? That's right, an infinite number of them. There's an infinite number of solutions to that. So here we're taking it up a notch because now we're going to do like systems of equations like that. Kind of like this. And I don't know if I'm letting the cat out of the bag too early here, but like a system, the word system, the fancy math word system of equations, all that means is more than one that are like together. And in high school, you're very rarely going to work with systems that have more than like 2 equations. Like this, 1, 2. 2 equations together make a system of equations. So the question here, what do you think it takes to be a solution to something like this, a system of 2 equations? And, I might as well take this as you think about that. I might as well sneak in a little comment that, Yes, this is still probably review. If all this looks familiar, if you're thinking to yourself, Mr. Falk, I already know how to work with these things, then I wouldn't be surprised, because we're still doing like review material from what you probably at least were introduced to in Algebra 1. But anyway, what do you think it takes? Like, describe a solution. Don't give me an example of one. Describe a solution to a system of two equations. A solution needs to be a pair of numbers that makes both of these equations true at the same time. Because remember, usually solutions are true. Both equations are linear. So now we're getting into like, okay, tell me what a solution would be. Give me a pair of numbers that makes both of these equations true. Well, that's easier said than done most of the time. So here's what we're going to do. Both equations are linear. Graph both lines on the same plane. And then maybe by looking at the graph, we can sort of think about like what the solution would be. Now, notice that both of these are not already in y equals mx plus b form. So this stuff right here is the little scratch work or the side work that we have to do in order to put both of these in y equals mx plus b form, so that we know the red line is going to have a y-intercept of -3 and a slope of -1/3. Meanwhile, the other line is going to have a y-intercept of what? 0. This might as well say +0. And the slope is going to be 2/3. So, okay, so when you plot those, and I didn't expect it to not be already great. Whoa. Just a bit outside. And so there are the so there's the full lines. So remember, so what would be the solution or the solutions to this system of two equations? Remember that the first line, we'll say the blue line, holds, well, yeah, whatever, it doesn't matter. We'll say the first line is the blue line. Remember that the blue line holds all the solutions to the blue equation. So all the solutions that make this equation true are literally on this blue line. Same thing with the other one. All of the solutions that make this red equation true, literally you can find on the red or pink line. So doesn't it make sense that whatever point is shared by both lines makes both equations true and solves both equations? So it's really going to be that easy, people. So here is the punchline for at least the first half of today's lesson. Okay, you can summarize the first half of today's lesson by pretty much this: where your two lines intersect, that is your answer. It's really that simple. So these two lines intersect at the point -3, -2. This is where mouse skills, not too shabby. That's not bad. So the final answer, and there's only one of them, so there's only one ordered pair in the whole world that makes both of these equations true and therefore solves the system: -3, -2. So this almost seems like we're doing this late, but here it is, and I guess it's already typed in here for you, because I already really said this. a linear system of equations, a set of two or more equations that use the same variables. They are considered together. And we're being a little repetitive here again, but a solution to a linear system is an ordered pair that solves both equations. So again, just being a little redundant here, but I mean they're major teaching points of today's lesson. So since we're just graphing, what if you had a graphing? What if you had a little technology to make your life easier? What if you had a little graphing calculator? I've probably at this point told you about Desmos.com. If I haven't already, I apologize, but I'm telling you now. Desmos.com, DESMOS.com, is a tremendous online graphing calculator, And, if you were graphing it yourself or throwing it into a graphing calculator, you would need to solve this blue equation for y, and you would need to solve this pink equation for y. And so really the final drafts would be this equation and this equation. But it turns out that with Desmos, not so much graphing calculators, but with Desmos, it looks like you can type it in as is from the beginning, Doesn't have to be in y equals mx plus b form on Desmos. And you can just throw that in really quick, and it graphs the lines. And you know what I like about Desmos Extra is that important points of note, like intercepts and points of intersection, if you put your cursor over it or whatever, if you click on something, it'll automatically tell you, hey, this is a pretty important point. It's where they cross. Just like if I were to click here or put my mouse here, it would tell me that that's 0, -2, and whatever the heck that is. But the point we're looking at here is 2, -1, and that would be our final answer. And so there's only one answer to this system, and it's 2, -1. All right, so that's kind of like the first big important part of today's lesson. The second sort of half talks about classifying linear systems, because guess what? You can classify a linear system by the number of solutions. So far in today's video, we've seen the classification called independent system, where there is one single solution, because our lines intersected at one point, which means there was one solution. So we call that independent. The system is independent. It's got intersecting lines, and there is one solution. Can you guys think of what one or both of the other two possible scenarios? What could be another scenario? What do you think? What do you think? Well, perhaps you thought of parallel lines, which, spoiler alert, sorry, let's go with navy blue. So just some kind of random, okay, two lines that were parallel, because that can happen. You could have two linear equations, making your system that would result in two parallel lines. Parallel lines do not share any points in common. They literally never touch. So that means that even though there's an infinite number of solutions to the one equation, as well as infinitely many solutions to the other equation, they don't share any in common, so therefore there's 0 solutions to the entire system. Okay? Now what's the third scenario? Oh, by the way, almost forgot. Hold on. Almost forgot. The official fancy title or label or whatever is that the system is inconsistent. It's completely inconsistent. It doesn't even have any solutions, so therefore it's inconsistent. I think that word fits. I don't think you'll have any problems or major problems anyway, remembering that inconsistent corresponds with 0 solutions. Think about it. This system is totally inconsistent. No solutions. It's inconsistent. What's the third scenario? What's the third scenario? Well, we could have, we could have some line, right? Let's make these a little, whoa, baby. We could have one line, just like that. And we could have a second equation that is graphed as a second line, but it's actually the same line. They are like coinciding lines. It's the same line. They completely overlap with each other. That's going to be called dependent. Okay? And how many solutions do you think there's going to be to the whole system? How many points do these two lines have in common? That's right. Infinitely many solutions. There are infinite solutions. So basically, any solution that solves one of the equations would solve the other one, because they're the same line. It's like they're the same equation in disguise. Okay? Anyway, so that's that. And the last little bit, well, basically the last bit is going to be questions like this. Could you think of a way to figure out what kind of system you were dealing with without actually literally graphing it, like without actually having to literally draw the lines? You look at it and go like, hey, okay, after actually drawing the lines, I see that they cross somewhere, or I see that these two lines, now that I've actually drawn them, are parallel, or I can now see with my own eyes beyond a shadow of a doubt that these two lines are actually the same exact line. Do you have to actually draw the lines to know whether or not they're going to be parallel, or they're going to be the same exact line, or they're going to be crossing somewhere? What are we going to do? Here's what we're going to do. We're going to sort of get in that mode, we're going to act like we're going to graph, which means we're going to actually solve the equation or the equations for y if you have to. So it looks like here you have to solve both of them. And when you do that, okay, I don't know if we need these arrows, but that one's becoming that eventually. And that one's becoming that eventually. This one becomes that one over here. And this one ultimately becomes that, and this, I don't know, you might even if you don't need to draw the arrows, if you kind of know what's up here. The bottom line is I've solved both of these for y. This equation was already solved for y, so I had to solve this equation for y in a couple of steps, and then I solved both of these equations for y. And then now that they're solved for y, look, let's just here in purple. Look at these. Y equals negative 3x plus 5, y equals negative 3x plus 0.4. What classification of system is this? Is it independent, inconsistent, or dependent? And how do you know? Well, hopefully you figured out that this is going to be an inconsistent system. If you were to graph these lines, they would be parallel and therefore 0 solution, so inconsistent. And the reason I know they're going to be parallel is just by looking at the equations, is that they have the same slopes but different y-intercepts. So you kind of get up to the brink of actually drawing the line. You don't have to act so you don't need graph paper, you don't need a grid, You don't need to actually draw the lines to know that they're going to be parallel, because, same slopes, different y-intercepts. So take a look at this. This was the equation number 1. This is what equation number 2 was rewritten as. So I told you, 2 equations could really be the exact same equation in disguise. So these end up being the exact same equations, which means they're going to be the exact same lines, which means dependent when that happens. All right? And here, what's going on here? What kind of system is this going to be? And you're probably thinking, well, by process of elimination, independent, right? Independent means one solution. That the 2 lines are going to cross in one spot. Well, how do you know that? Just by looking at the equations. That's right. Each equation has a totally different slope. If 2 lines have different slopes, they're going to cross somewhere. I don't really know where that is right now. Remember, in these 3 problems, I'm not asking you for the solution. I was just asking, what kind of system is it? How do you classify? Like, what's the classification? So, again, you would just make sure both equations were solved for y, and then based on what you see with the slopes and the y-intercepts, you can pretty much figure out what kind of graphs you're going to have, and therefore what kind of system, and therefore how many solutions, right? 0 solutions, infinitely many solutions, and 1 solution. And this right here is just kind of like a little bit of foreshadowing to tomorrow's lesson or next time we're together's lesson. So right now we've covered graphing as a method for solving a linear system. Or at least setting up the equations to the point where you know what the graphs would look like. Yeah, so, the only method for solving is like literally graphing, or, if you solve both of them for y, and you see that, oh my gosh, I don't need to actually graph these lines. They're going to be parallel, So I don't need to actually draw the lines to know that there's going to be 0 solutions. But, you graph when you can see that there's going to be 1 solution, right? And you graph it so you can find out what it is, basically. But that's it. That's section 3.1.